Now we have the same exercise, and we start again from the state output table. I told you that we can assume that the state output table cannot be reduced anymore, and those states are essential. And now the difference is that I have used a second assignment. Instead of use a correlative order, I have just followed the rules of the code assignment, the rules that I'm going to tell you later. According to these rules, we have to use this code to codify the different states of the system. So with this code, using the state output table, we can build the transition table. So I have keep the correlative number here in the columns, but now they represent different states that are specified here in this table. So if we are in the state 4, because 4 is 0, 0, 0, 0, we are in state 4, we check what happens here. From state 4 we go to 2 and 5. 2 is 1, 0, 1 and 5, 0, 0, 1. So we go to 1, 0, 1 and 0, 0, 1 that are 2 and 5. If we continue looking at the state output table and the codification we have chosen, we build the transition table. Now, using the transition table of the circuits we are designing and the evolution table of the base table we have to use, we build the excitation table. Remember, the excitation table is telling us what do we have to put in the input to have the behavior specified here in the transition table. Because we are using the base table, in a the base table, if we want a specific desired net state, we only have to put that value in the input of the base table. So the input of the base table is going to be the same value of the net state. So we can copy, we can copy both tables. Both tables are the same. And using the excitation table, we build the 3 Karnaugh maps we need for the 3 base table, and we obtain the logic function we have to implement with gates. So again, let me to build the Karnaugh maps using the excitation table. So now I have obtained these 3 Karnaugh maps using the excitation table information. Again, for example, if I'm going to give you some example using the input of the base table 2. For this column, we have that x is 0 and y is 0. So x is 0 here and y1 is 0 here. So the value of d2 in those cells are, the values are 0, 1, 0, x, 0, 1, 0, x. Well, we can see here that the don't care conditions are in different combination as before, because if we use these codifications, the variables, the codification that are not used are the 0, 1, 1 and the 1, 1, 1. So here we write the x, the don't care condition. So once we have the Karnaugh maps, we obtain the function of the input of the base tables. And now you can see that, for example, here we have this prime implicant and this prime implicant. Sorry, I don't know why I didn't write. And this prime implicant that can be I1, I2. In D2 we have this prime implicant that can be, for example, implicant 3, and for D3 we have just this prime implicant that we can call I4. So we have that D1 is just I1 plus I2, and D2 we have just I3, and here we have just I4. And you can see that this logic, this combinational circuit that we have to connect before each bistable, when we implement the logic circuit here in these gaps, this function are much simpler than the ones we obtained before. So we are going to save a lot of cost, and this simplification has been done just changing the code we assigned to each state of the circuit. Both versions, this and the previous one, does exactly the same function on the circuits, because the circuits are the same, but this is much simpler. So these combinational circuits are going to be much simpler with this state assignment. In order to reach that, we have to apply the rules that we are going to see here. Rules for the assignment of the state variables. We are going to see the rules that are these 4 rules: 1a, 1b, 1c, 2, and 3. And these rules are going to be applied in a hierarchical order. So, for example, if we have here one condition for 2 states, and we have here a different condition for the same state, we are going to apply this condition because this is going to be more efficient than this one. So we are going to follow this order when applying the rules. So these rules are based in the concept of adjacency. We saw the concept of adjacency when learning about the Karnaugh map, and we saw that two words in a code are adjacent if they only differs in one of their bits. For example, here A and B are adjacent because only one bit, 0 here and 1 here, are different. So A and B are adjacent. We are going to look for the adjacency or specific states to have later, after the codification, the minimum combinational circuit. So the rules are these ones. I'm going to explain you the rules one by one. So we start with the rule 1a, and this rule says that the states with identical net states have to be adjacent. So we are going to assign codes that are adjacent, code that only differs in 1 bit, to those states for which the net state for all the inputs are identical. So I'm going to give you an example of this. For example, if we have this state output table with only 1 input and 2 states, A and B, so the input can be 1 and 0. And here, for example, the net state for A are C and E. This is a B, sorry. And for B are C and E. You can see here that in this really small state table, the net state for all the inputs of A and B are the same. So according to the first rule, A and B should be adjacent, should have adjacent codifications. For example, imagine that we have here more states, so finally we have 8 states and we have 3 state variables. It means that, for example, if I assign this value to A, I have to assign, for example, this value to B, or this value to B, or this value, because in all of these cases, only one bit differs from the codification of A. We are going to see, the second rule, that is 1B. So in this case, the state with identical net state for all inputs, but now in different inputs, should have adjacent assignment only if the net state can be given as well as adjacent assignment. So again, I'm going to give you an example of the rule 1B. So imagine we have this state output table. I'm not writing the output either because they are not important here. But in a real state output table, we have to write the output as well. So we have here the state A, B, C, and for example, for B and C, the net states are A and F. But in this case, the states are the same, but in different outputs. In this case, of the first rule, they have the same net state for the same outputs. But here, they have the same net state for different outputs. For 0, B has A and C has F, and for 1, B has F and C has A. So in this case, according to the rule 1B, state B and C should have adjacent assignment only if we can give adjacent assignment to the net state, to the net states that are A and F. If I cannot give adjacent assignment to A and F, we don't have to fulfill this condition. For example, if A and F can be these that are adjacent, in this case, we have to give adjacent assignments to, for example, B and C. Do you see it? A and A and F are adjacent because only this bit differs. So B and C have adjacent codification because we have that the net states are adjacent. I'm going to tell you a thing in advance, and is that we are not going to be able to meet all the conditions. We are going to have some condition outs because it's impossible with the state we have and the combination we have to fulfill all the conditions. So sometimes we have to rule out or not to take into account some of the specification given by the rules. For example, imagine that in applying the rule 1B, the rule 1B says that B and C have to be in a way, but the rule 1A says that the B and C has to be assigned using a different way. In this case, we have to do what is specified by rule 1A because rule 1A has a higher priority. That's the thing that I told you about the hierarchy of the rules. So we are going to continue with the rule 1C now. Rule 1C, says that a state with identical net state, at least for some inputs, should have adjacent assignment. And you know, the more inputs they have the same, the higher the priority the adjacency of this state should have. So again, I'm going to give you an example. So for rule C, we are going to imagine that we have this state output table. Here we have the input, one input that is X, and here we have the states A, B, C are more states. And we have this next state for this current state. Here we are not fulfilling neither rule 1a nor rule 1b. But here we have that this state for some of their inputs, specifically for 0, they have net states that are the same. So according to rule 3, state A, B, and C should have adjacent assignment, adjacent codes. The adjacency is given by pairs, so we cannot have this. This is a way of express that A is adjacent with B, A is adjacent with C, and B is adjacent with C. We can summarize this using this, but the adjacency is always given in pairs. So we should find adjacent codes for the states A, B, and C. For example, and B have to be adjacent with both of them. So you have to be sorry. C had to be adjacent with both of them. So you have to be careful. For example, we can use for C 1, 1, 1. That only differs in one bit with A and in one bit with B. So the three of them are adjacent. This is rule C. And I'm going to need more space to explain rules 2 and 3. So I'm going to clear this. So rule 2 is quite simple. It says that the net state of the same state should have adjacent assignment. You can see that as we go further with the rule, the conditions are easier to fulfill. So rule 2, the net state of the same state should have adjacent assignment. Quite easy. Rule 2. Example, we have this state output table. And Q. So we have these 3 and the table continues. A, B, and C. And they have, for example, these nest states. So according to rule 2, the net state of the same state has to be adjacent. The net state of A are B and D, so they should be adjacent. The net state of B are A and F, so they should be adjacent. And the net state of C are A and F. So according to these rules, we have to assign codes here fulfilling these adjacencies. And finally, we have rule 3. Rule 3 is this one, and it says that states that have the same output for a certain input should have adjacent assignment. I mean, just having the same output for one of the inputs, we have fulfilled this rule. You know, it's quite easy to fulfill. But this rule is going to get a worse circuit as if we apply, for example, rule 1a, because we have to take into account always this priority. So when we have the state output table, we are going to assign the codes in this order, fulfilling 1a, 1b, 1c, rule 2, and rule 3. Imagine that just applying 1a and 1b, we have all the state coded. We don't have to follow with the rest of them because 1 and b are more important. So even if we are going to identify all the rules, we are going to apply the higher rules as much as possible. So we are going to see this with a real example. So imagine we have this state output table because we are designing a sequential circuit. So we build the state the state transition diagram with the circles and the arcs, and from the state transition diagram we obtain the state output table. We have applied the method of the reduction of the number of states, and finally we have this state that cannot be reduced anymore. So we have to codify them in order to build the transition table. In the transition table, as you know, we have zeros and ones. We have here 7 states. If we have 7 states, how many state variables do we have to use? For 7, we have to use 3 state variables that are going to allow to us to codify 8 states. We are not going to use all the codes, but we have to use at least 3 state variables that can be, for example, y2, y1, or y0, for example. So now we are going to apply the rules to know which code between 0, 0, 0 and 1, 1, 1 we are going to apply we are going to use for codifying any states. So we start always with the rules 1a, that is the one with the highest priority. So a state with identical net state for all the inputs in the same input, important, should have adjacent assignment. So if we look at the table, we can see that a state with the same net state for the same input are D and F, for example, for which inputs are FF, CC. If we look more, we have that, for example, E and G have the same net state for the same input. Remember, rule 1, the same input. So according to the rule 1a, we have that the state D and F and the state E and G should be adjacent when codifying. So we cannot apply rule 1a anymore. So we proceed with the rule 1b. So rule 1b that affects a state with identical net state for all inputs, but now in different inputs. So we look at our table. If we look at the table, we don't have a state with the same net state, but with the input changes. We don't have that kind of state, so we cannot apply rule 1b in this state output table. So 1b is not useful here. We proceed with the rule 1c. The rule 1c says that the state with identical net state for just some input should have adjacent assignments. So we are going to look for this kind of pairs of states. So if we look at the net states, we have that. I'm going to remove this. We have that for the input x0, A, C, E, and G have the same net state, that is B. So remember, the net state for some input, in this case input x equals to 0. So this for state should be adjacent, and the state and for x equal to 1, no, here for x equal to 0, we still have that D and F have the same state, so they should be adjacent. So I'm going to write this: for the input s equal to 0, A, C, E, and G should be adjacent. Besides, the states D and F, because all of these shares the net state B, and all of these two shares the net state F. Okay? So we can apply the same rule for x equal to 1. For x equal to 1, we have that state A, B, C, D and F have the same net state C. And the state E and D have the same state G. So for x equal to 1, we have that A, B, D, and F should have adjacent codifications, and as well D and E. Sorry, this is not good. I made a mistake here. The state E and G have the same net state G, and these ones have the same state C. So we have to fulfill these adjacencies when applying the rule 1C. I have to remember the following: these states have to be adjacent in pairs. That is, AC, A with E, A with this is J, I don't remember. Yes, it's G. C with E, C with G, and E with G. It's extracting all the possible pairs of these adjacencies. Okay. We have the same with this. This means that A have to be adjacent with B, A with D, A with F, B with D, B with F, and D with F. Okay, all the possible combinations in pairs that we can extract from this adjacency. So now we apply the rule 2. The net state of the same state should have adjacent assignment. This is quite easy to apply. Rule 2. The net state of A are BC. The net state of B are DC. The net state of C are BE. The net state of D are D are FC. The net state of E are BG. The net state of F are FC, that is repeated, and the net state of G are BG, that is also repeated. So this is rule 2. The net state of the same state should be adjacent. And finally, we apply rule 3. And rule 3 is that states that have the same output for a certain input should have adjacent assignment. So if we look at the output that are here, for x equal to 0, all the states have the same output, that is 0. So all the states should be adjacent with all. All with all. And for x equal to 1, we have different outputs. We have some state with output 1 and some state with output 0. And here we have an errata in the table, because when I write in the table, this program, this software, sometimes corrects my writing and introduces mistakes. And here, this circle is really a 1. So, for x equals to 1, the state with the same output are A, B, C, F, and E, because all share output 1. And for output 0, we have C and G, because they have output 0. Sorry, this is D and G. So you can see that it's impossible to fulfill all these conditions. It's impossible. If we, in some cases, if we codify to a state with adjacent codes, we cannot fulfill the same assignment in other rules. So we are going to start, as I told you, from the first rule to the last rule. And how do we do the assignment? We are going to use a Karnaugh map. Why? Because we saw that in a Karnaugh map, those cells that are together, the cells that are together just horizontally or vertically, are adjacent, has codes that are adjacent because of the gray codifications. So it's going to be really useful for this codification, use Karnaugh map. Since we have 3 state variables, we have y2, y1, and y0, we are going to build a Karnaugh map of 3 variables, just this way. Karnaugh map with 3 variables. Starting with the most significant bit and using, as you know, gray code. So we are going to start with the rule 1, and here we have freedom to choose the codes. We have to fulfill as many conditions as possible, but we are free to choose the combinations. So we have that for rule 1a, D has to be adjacent with F, and E has to be adjacent with F. So for example, I can write here D, F had to be adjacent, so F had to be here, here, or here. I'm going to choose, for example, F here. So we have fulfilled this condition. And now we are going to make E and G adjacent. So I can choose, for example, this for E, and G have to be here or here to be adjacent with E. So for example, I am going to choose this cell for G. So the first 2 rules, the first 2 conditions of the first rules are fulfilled. We cannot apply rule 1b in this example, so we are going to start applying the rule 1c. 1c. So let's see. We have to to fulfill all these conditions. Maybe, well, when I say maybe, is almost never we are going to be able to fulfill all of them. So I'm going to choose, for example, for A this cell, and for B this cell. If I choose these two cells, I have that A is adjacent with B, so I fulfilling this condition, and A is as well adjacent with G, so I'm fulfilling this condition. Do you see it? It's adjacent with G because of the vertical cells. And what happened with B? With this codification, B is adjacent with F, so we are fulfilling this condition. And I mean, don't feel overwhelmed because it's not possible to fulfill all the conditions, so take it easy. So I'm going to choose, for example, for C this gap, and in this case, if I choose this gap, I have that A is adjacent with C, fulfilling this condition. A is adjacent with E, fulfilling this condition, and C is adjacent with F, and with F, CF. Well, in this case, this condition is not in the rule, but it doesn't matter. I mean, it's difficult to fulfill because the combinations are quite limited. So at this point we have finished the assignment. Well, I see that no, well, sorry, I don't see more conditions that we have fulfilled, but we have finished. We don't have to continue with rules 2 and 3 because just applying rule 1A and 1C, we have all the state as with its assignments. So now A is going to be 0, 0, 0. B is going to be 1, 0, 0. C is going to be 0, 0, 1. D is going to be 1, 1, 1. E is 0, 1, 1. F is 1, 0, 1. And G is 0, 1, 0. So we have finished the assignment of the code to the state, and we can build the state the transition table. Now I'm going to choose a different assignment just to show you that this is not, you know, a fixed solution. We can have several solutions, and maybe when doing some exercise you don't find the optimal and best solution, or another student find a better solution than yours. You have to apply the rules carefully to try to get the most optimal solution, but you have some freedom to assign this code. So I'm going to remove this assignment to choose a different assignment. So I'm going to delete this. And for example, now we are going to assign, starting with the first rule again, D and F this way. D and F. So D and F are adjacent. They are adjacent. And now I'm going to use for E and G. Sorry. For E and G. These cells, and both of them are adjacent, so we have fulfilled the first rule. And now for A and B, these two, and with this assignment A is adjacent with E. We have fulfilled this condition. With D, that we have fulfilled this condition. With B, and B is adjacent with G. We don't have that anywhere. With F, that we don't have either that condition. With F, yes, we have here. And finally, I have to assign C. I can use, for example, this cell. So we have that C is adjacent with D and with E. So with E, we have fulfilled this condition. So now our code would be A is 0, 0, 1, B is 1, 0, 1, C is 0, 1, 0, D is 0, 1, 1, E is 0, 0, 0, F is 1, 1, 1, and G is 1, 0, 0. So we have this different assignment. In fact, we have fulfilled the same number of conditions. So we are going to have the same, minimized combinational circuit in the input or the bytes table. So, well, these are the rules to assign the codes to the states. We have to learn the rules, identifying the adjacencies, and apply all the adjacencies that we can, always using this hierarchical order. Note that with again, with one C rule, we have complete all the assignments. So it's possible that we don't reach the rules 2 and 3 in our assignment. We don't know this beforehand, but it can happen. So now we have all the tools to design a sequential circuit. So what I'm going to do is just to continue with the example of the binary adder that we saw some lessons ago. In this example, we advance until the transition table. So in the transition table, we have to assign the states and obtain the excitation table, and from the excitation table, implement the combinational circuit at the input of the memory element. So I'm going to clear this, copy all of the binary adder until the point with it, and continue with the design of the circuit. Just let me clear this. So this is what we did with the example of the binary adder. So we are going to see this slide because we have just all the elements to do the design of a sequential circuit. So we are going to see all the steps of this algorithm. So the first step is to identify the input, output, and the input-output behavior based on the problem description. That is to say, we identify the input, the output, and the state of the circuit. So step 1. Here, in a binary adder, we have identified that we have two inputs that can cover all these combinations. The input are A and B. The output is going to be S, the result of the sum, and the possible states are going to be Q0 or Q1. Q0 means that the carry is 0, and Q1 means that the carry is 1. The carry was the thing that our circuit has to memorize from one state to the next. We have the first stage. The first stage, that is the 1. We have the second stage, the stage or step. We can use both words. The second step is to design the state machine that verifies the behavior of the circuit. We can use a milli or a Moore. So here we have the state transition diagram. We are going to have two cycles because we have two states, and according to the inputs we are going to have one transition or another and one possible output. Remember that we add here this arc with the meaning of the values in the arcs. So the values are going to be the values of the input A and B and the output for this transition. Remember that if we have, for example, this transition, if we have that the carry is 0 and we receive 1, 1, 1 plus 1, we have that the sum bit is 0 and the carry is 1. So we are in this state in which the carry is 1. We did this in class. So I guess that you know how to do it. From the state transition diagram, that is the stage 2, we are going to do the next stage, that is specify the state output table that we have here. In a melee machine, as the one we have here, we have that the output depends on both the state and the input. So we have to specify in itself the net state but also the output. Here we are going to have the net state but also the output. So looking at the state transition diagram, we can build this table. If we are in the state Q0 and we receive 0, 0, we are here. If we receive 0, 0, we go to the same state Q0 and the output is going to be 0. We are in this cell. So following all the transitions for all of the inputs, we are going to fill the table with the net states of each transition and the output for that transition. So we have fulfilled stage 3 or step 3. The step 4, reduce the number of states, applying the method of the implication chart. But what happened here? We have only 2 states. It's impossible to reduce the number of states. We have 2. In a sequential circuit, we are going to have at least 2 states. I mean, that's obvious. So we don't have to apply step 4. Step 5 is to use an appropriate code assignment using the rules that we have just seen. But what happened? That we have only 2 states, so we don't have more possibilities. One state has to be 0 and the other 1. This is quite obvious. So we cannot apply here the rules of the code assignment. So we can directly obtain the transition table using this codification. Remember that the transition table has the net state in the cells, not the output, only the net state, but instead of using the name that we assign to the state, that here is Q0 and Q1, we are going to use directly the code assigned to this state. So in this example, Q0 is 0 and Q1 is 1. So if we see as the state output table, if we are in Q0, that is 0, the net state are going to be Q0, Q0, Q1, Q0. That is 0, 0, 1, 0. 0, 0, 1, 0. If we are here in the current state Q1, that is 1, we have that the net state are Q0, Q1, Q1, Q1. That is 0, 1, 1, 1. 0, 1, 1, 1. So we already have the transition table. We did all this some lesson ago, so just refresh it if you need it. The new thing that we are going to add here is the calculation of the excitation table to have the logic circuit that implements this binary adder. So the next stage is to obtain the excitation table. In order to do that, we need the evolution table of the memory element that we are going to use. And imagine that in this case we have told that we have to use for example JK bistable. The evolution table of a JK bistable was a mix between the SR and the t bistable. If you don't remember the evolution table, you can deduce this table from the behavior table that you have to learn by heart. So we have this in this case. In order to obtain this evolution, the input has to be the following. Remember that when we have an x in the input, it means that we are going to obtain the same evolution either if the value is 1 or 0. So for example here, if we need that evolution from the current state to the next state is from 1 to 0, k has to be 1, but j can be either 0 or 1. So it's more flexible in this case. So using these two tables, the table of the target circuit and the evolution table of the memory element we have to use, we built the excitation table. Remember that the excitation table is the same, have the same input of the transition table. Here we have the input A and B in the binary order in gray code, and here we have the state variable. But what we have in the cells are the inputs of the bistable that we are going to use as memory element. So in order to fill this table, we have to look at the rows, just the rows, not the columns, just the rows of the transition table and to the evolution table. So we are going to go row by row. In the first cells, we are transitioning from 0 to 0. From 0 to 0, to have this behavior, we need that the input of the JK bistable be 0x. So we write here 0x. And in fact, every time that we transition from 0 to 0, we need this input. So from 0 to 0, we are going to be in this cell, in this cell, and in this cell. So the input has to be the same in these three cases. What happens if the transition is from 0, I'm going to change the color, from 0 to 1. From 0 to 1, we are here in this row. So to have this evolution, we need that the input of the JK bistable be 1x. And now we are going to look at the other row of the transition table. So if the transition is from 1 to 0, we are here. The input of the JK bistable have to be x1. So x1. We are just configuring the input of the bistable we are going to use to obtain this behavior, that is the desired behavior. So the other possibility is that the evolution of the state are from 1 to 1. From 1 to 1, we are in these three cells. In this case, we are in this row of the evolution table. So we need that the input of the JK bistable be x0. So for the three cells, we write x0. So we already have the excitation table of our circuits. And as I told you, this is the most important step of the design. So here we may build two Karnaugh maps, one for the J and another one for the K, just copying here the first values and copying here the second values, or we can use directly this. If I want to obtain the function of the J, we have to look at the first value. So for the J, I have only a 1 that is here, so I can form this for an implicant. And for the case of the k, we have as well only a 1 that is here, so I can form only these prime implicants. So you can see that they are quite easy. J is going to be this product term that is A, B, and K is going to be the other product term that is A negated, B negated. So we have almost finished the implementation, but I need some space, so let me clear some of the information we have in the screen. So now I have more space. So we have to use a JK base table. How many state variables do we have? Just one, A0. Just one, so we only need one JK base table. So I draw the JK base table. So remember that we have the two inputs, J and K, and we have always the state variable and the state variable negated. This is of state variables is 0. So we have that J have to be an AND gate of the input of the other, A and B, and K is going to be the AND gate of the inputs of the other but negated. What happens with the output? Because until now we don't have the output of the circuit. We have to build the output of the circuit. It's quite easy. We have to look at the state output table. It's the only table in which we have the output. So here the table is a Karnaugh map. No, it's a Karnaugh map. It's codified in gray code, etc. So we obtain the function. Which are the prime implicants we have here? Well, we cannot do a lot. We have this prime implicant. So we calculate the output. So according to those prime implicants, we have that the output is the following. If you apply here your knowledge about logic gate and the Boolean algebra, you can have that we can write the above expression like the XOR of A, B and Y0. If you don't know how to pass from here to here, just let me know, ask, I'll tell you the step. Okay? So in order to obtain the output of the circuit, we have an XOR gate of 3 inputs. One input is the state variable of the base table, and the other input are A and B. So we have finished. This circuit is the binary adder that performs the function that we were told in the beginning of the exercise. So we have just finished our first design circuit, starting with some specification in natural language and finishing with the logic circuit. Well, I was telling the different steps, but I forgot to write the step 6, 7, etc. But we can follow them here. The 6th step is to obtain the transition table. the seventh step is choose the type of bistable, but I told you that normally you are told the bistable you have to use. It's not a matter of choosing it. And once you have the transition table and the kind of bistable, with the evolution table you establish the excitation table. And once you have this, you minimize the functions and obtain the final circuit diagram. Now we are going to do an analysis of a sequential circuit. In this case, we have this, not this, but another logic circuit, and we have to do the steps in the opposite order until we obtain the state transition diagram. So I'm going to give you a logic circuit, and we are going to do the step in the opposite order that are here. So just let me to clear this and draw the logic circuit we are going to use.